So recall that the set of quaternions is the set of all numbers of the form x sub 1 plus x sub 2 times I plus x sub 3 times j plus x sub 4 times k, where the numbers x sub I are real numbers, and the numbers 1, I, j, and k are quaternion units, where the fundamental equation relating these units is I squared is the same as j squared, which is the same as k squared, which is the same as the product I times j times k, which is -1. And also recall that for every element in this set, this element can be written as x sub 1 plus x sub 2 times I plus the quantity x sub 3 plus x sub 4 times I times j, since I times j is the unit k. And so this is a complex linear combination, including a complex multiple of the number j. And so the set of quaternions can be considered an algebraic extension of the complex numbers. And this is the set of all numbers of the form x plus y times j, where x and y are complex numbers, and j squared is -1. So next we will show that this algebraic extension of the complex numbers is a vector space over the field of complex numbers. And in this set of vectors, we have a notion of vector addition. The vector x sub 1 plus y sub 1 times j plus the vector x sub 2 plus y sub 2 times j is the vector x sub 1 plus x sub 2 plus the quantity y sub 1 plus y sub 2 times j. And we also have a notion of vector scalar multiplication. The scalar a, where again the scalar is a complex number, times the vector x plus y times j, is the vector a times x plus a times y times j. So let h sub I be a vector in this set. Then the sum h sub 1 plus h sub 2, again, is the sum of vectors x sub 1 plus y sub 1 times j, y sub 1 times j, plus x sub 2 plus y sub 2 times j. And this is the vector x sub 1 plus x sub 2 plus the quantity y sub 1 plus y sub 2 times j. And this is the same as x sub 2 plus x sub 1 plus the quantity y sub 2 plus y sub 1 times j, which is the sum h sub 2 plus h sub 1. Now clearly, the sum of two complex numbers is once again a complex number. And so addition is both closed and commutative. Over this set of vectors. Now the sum h sub 1 plus the quantity h sub 2 plus h sub 3 is the sum of vectors x sub 1 plus y sub 1 times j plus x sub 2 plus x sub 3 plus the quantity y sub 2 plus y sub 3 times j. This is the same as x sub 1 plus x sub 2 plus x sub 3 plus the quantity y sub 1 plus y sub 2 plus y sub 3 times j. And this is the same as the quantity x sub 1 plus x sub 2 plus the quantity y sub 1 plus y sub 2 times j plus the vector x sub 3 plus y sub 3 times j. And this is the quantity h sub 1 plus h sub 2 plus h sub 3. And so addition is associative over this set of vectors. Now there exists the complex number 0, which can be written in the form 0 plus 0 times j. In this set of vectors, such that for every element or every vector in this set, we have that 0 plus the vector h is the vector 0 plus 0j plus x plus y times j. And this is 0 plus x plus the quantity 0 plus y times j, which is x plus y times j, which is the vector h. So as multiplication, or rather as addition, is commutative, we have that 0 plus h is the same as h plus 0, which is h. And for every vector h in this set, we have the negative of that vector, which is also in the set, such that h plus its negative is the sum of vectors x plus y times j plus negative x plus negative y times j, which is x plus negative x plus the quantity y plus negative y times j, which is 0 plus 0 times j, which is the additive identity. And so this set of vectors, the algebraic extension of the complex numbers to include complex multiples of the number j, under addition, is an abelian group. So let A and B be complex numbers that are that is the scalar field, and let h sub I be a vector. Then the product, scalar product of A with the vector h is the scalar A times the vector x plus y times j, which is the vector A times x plus A times y times j, where the product A times x and A times y are complex numbers, since the complex numbers is a field, as a set is a field, and so it is closed under multiplication. And so the product, the scalar product, is once again a vector. Now, The sum of scalars a plus b times the vector h is the sum of scalars times the vector x plus y times j. And this is the scalar a plus b times x plus the scalar a plus b times y times j. And this gives us a times x plus b times x plus a times y times j plus b times y times j. And we can regroup these terms so that we have those that contain the scalar a together, so that we have a times x plus a times y times j plus b times x plus b times y times j. This is a times the vector x plus y times j plus b times the vector x plus y times j, which is a times the vector h plus b times the vector h. And so a sum of scalars distributes over a vector. Now, the scalar a times the sum of vectors h sub 1 plus h sub 2 is the scalar a times the vector x sub 1 plus x sub 2 plus the quantity y sub 1 plus y sub 2 times j. This is the scalar a times the quantity x sub 1 plus x sub 2 plus a times the quantity y sub 1 plus y sub 2 times j. And this gives us a times x sub 1 plus a times x sub 2 plus a times y sub 1 times j plus a times y sub 2 times j. And so we have that a times h sub 1 plus h sub 2 is a times x sub 1 plus a times y sub 1 times j plus a times x sub 2 plus a times y sub 2 times j. And this is the scalar a times the vector x sub 1 plus y sub 1 times j plus a times the vector x sub 2 plus y sub 2 times j. And this is a times the vector h sub 1 plus a times the vector h sub 2. And so a scalar distributes over a sum of vectors. So now we look at the product of scalars a times b times the vector h. This is the scalar a times b times the vector x plus y times j. And so this is the scalar a times b times x plus a times b times y times j. So this is a times the vector b times x plus b times y times j, which is a times the vector bh. Now there exists the scalar 1, the complex number 1, such that for every vector we have that 1 times h is 1 times the vector x plus y times j, which is 1 times x plus 1 times y times j, which is x plus y times j, which is the vector h. And so all axioms for a vector space are satisfied. And so the algebraic extension of the complex numbers to include complex multiples of the number j is a vector space over the field of complex numbers. So notice that the combination A times 1 plus B times J is the scalar 0, or the vector 0, if and only if both the scalars A and B are 0. And so the vector 1 and the vector J are linearly independent. And for every vector in the vector space, that vector is a linear combination of the vectors 1 and j. And so the span of the set containing the vector 1 and the vector j is the entire space. And so a basis for the complex vector space is the set B, which contains the vector 1 and the vector j. Now, just as with the complex numbers over the field of real numbers, the set of quaternions can also be considered as a vector space consisting of ordered pairs of complex numbers, so the coordinate space of complex numbers, where we have a notion of vector addition, that is the vector x1, y1, plus the vector x2, y2 is the vector x1 plus x sub 2 as the first coordinate, and y sub 1 plus y sub 2 as the second coordinate. We also have a notion of scalar multiplication. The scalar a times the vector xy is the vector whose first component is a times x and whose second component is a times y, or as a coordinate space we can say the first and second coordinate. And here, notice that the scalar a times the vector 1, 0 plus b times the vector 0, 1 is the vector 0, 0 if and only if both scalars a and b are 0, and so the vector 1, 0 and 0, 1 are linearly independent. And for every vector considered as the coordinate space, we have that vector is a linear combination of the vectors 1, 0 and 0, 1 for some choice of scalars a and b, which again are complex numbers. So a basis for the complex vector space of the quaternions considered as the coordinate space containing ordered pairs of complex numbers is the set B, which contains the vectors 1, 0 and 0, 1. And so the dimension of the quaternions as a complex vector space is 2. Alright, so we'll end here for today. Next time we will look at the quaternions as a real vector space, and we will look at how the quaternions describe rotations of vectors in 4-dimensional and 3-dimensional space. So I hope you have enjoyed the 13th lecture. Thanks for watching.